Diversification distributes a system's total load or exposure across n independent subsystems. When components are independent, the variance of the aggregate output scales as 1 over n, the variance of the mean of n independent random variables. This is a statistical operation exploiting the law of large numbers. As n increases, the aggregate converges to its mean. No individual component changes its behavior, only the aggregate distribution narrows. Diversification reduces idiosyncratic variance but provides no protection against systemic or correlated variance. In a series system, the structure function is the product of all component states. Any single failure drives the system to zero. In a parallel system, the structure function is the complement of the product of component failure states. All components must fail for the system to fail. These two topologies define fundamentally different relationships between component failure and system failure. The series topology creates single-point failure modes. The parallel topology eliminates them at the cost of requiring simultaneous failure. Redundancy changes the topology of failure, not the statistics of individual component reliability. In a series system, a single component failure is sufficient to transition the full system to the absorbing failure state. No remaining components can restore operation. The transition is irreversible under normal dynamics. In a parallel system, the absorbing failure state requires that all n components fail simultaneously. The system topology therefore determines the conditions under which the absorbing state is reachable. Eliminating single-point failure modes is a topological design decision, not a component-level reliability decision. When n components are independent, the probability of joint failure scales as p to the power of n, becoming negligible for large n. When components are correlated, joint failure probability does not decrease below the common cause failure rate. Variance reduction from averaging also fails under correlation. The variance of the mean does not scale as 1 over n when components share a common shock. Redundancy provides its full structural benefit only under independence. Correlation between components is the structural property that neutralizes the protection redundancy is designed to provide. Expected performance optimization selects the design that maximizes mean output over the full distribution, including low probability failure states. Survival optimization conditions on the system remaining in the operating set and excludes the absorbing failure state from the performance average. These are structurally different objectives. The first tolerates catastrophic outcomes when sufficiently improbable. The second does not. Redundancy is structurally motivated by survival, by keeping the system outside the absorbing state. Adding redundancy to maximize expected performance is a different design choice and may yield different architectures. Redundancy provides structural protection against independent component failures by making joint failure exponentially unlikely. It reduces single-point failure modes by requiring simultaneous failure of all parallel components. However, when all components share a common failure mode, a shared environment, shared material, or common cause shock, redundancy provides no additional protection. Every redundant component fails along with the original at the same moment. Common cause failures are the structural limit of redundancy. They expose the system to the absorbing state regardless of how many parallel components are present.